Okay, good. So last time we stopped on computing the Poincare dual to certain classes. So let me just recall you. So what we have? So we have a manifold M of dimension n, and inside we have a submanifold of dimension k. And if it's closed, then what can we do? We can take cohomology class. Oh, here, yeah. So we can take a cohomology class of HK. Wait, so here it's. So we can integrate over n the compact classes, right? So omega, where omega belongs to HK with compact support. And so it means that we get an element in H. So, okay, so here it's K. And here it's n minus K. Okay, so since we have a map from case cohomologies with compact support to real numbers by this integration, right? So it means that it gives us an element of dual space, and the dual space by Poincare duality is Hn minus K. Good. And if we consider a closed submanifold, a compact submanifold, then we can pair exactly in the same way, but with cohomology, I mean, just of dimension k. And so dual space is cohomology of dimension n minus k. Okay, but now with compact support, so here we also need something like that M has a good covering. So for example, M is compact manifold, then it's automatically like that. Or it may be like a non-compact manifold, but let's say connected and with ends which are modeled by like, Rn. Okay, so and also we have a map from Hn minus k to Hn minus k with compact support to non-compact support. I mean, to just any support. And well, this map might be different, right? Sometimes it sends everything to zero, sometimes not. So it's generally these two spaces are any spaces. They may have relation, but the only relation for sure that there is a map. Okay, then we have a problem. We had to compute it for n equals r square without zero. So it's n equals to 2. And our n was just a array emanating from 0 to infinity. Okay. And okay, who succeeded? Who tried to do it?
I suppose that I did.
Okay. So let's consider.
I can share screen and
okay, so let's do it. So if you
show the solution. Yeah. Just a few seconds to.
Okay, let's do it. So definitely.
Can't resume from my iPad.
Okay, let's see.
Just a second. I suppose that I'm showing my screen.
Yeah.
Okay, we had on the last lecture, we wanted to show that the Poincare dual of the submanifold S, like this, the ray is the form d theta divided by 2p. So that was some calculations. Okay, let's take any closed form omega with the compact support and write it in polar coordinates like this. Yeah. Then since it's closed, since it is closed, we have the equality of the partial derivatives. Yeah. Then we wanted to show that the integral of the pullback along the inclusion is equal to the integral of omega, which d theta divided by 2p. This integral is equal to this integral, yeah? So, and this integral was equal to this integral. So it was enough to show that these two integrals are equal, yeah? Okay, it's just like elementary calculation. If the f does not depend of theta, it's obvious, yeah? So the integration by theta is just like 2p, 2p, and 2p, and we have what we need. But f can depend of theta. But this integral, if the form is closed, doesn't depend of theta. Why? Let's consider the function h of theta like this integration of f from 0 to infinity by dr and calculate the derivative by theta. It is equal to the integral of the derivative, and then we can use the equality of partial derivatives. Yeah.
Well, maybe you also have minus there, right? And, you know, in the inequality of partial derivatives, you know, if the form is closed, maybe you have minus there.
I suppose that it doesn't matter in this calculation.
It doesn't matter, but let's first agree on that. So do you agree that we should write minus here?
Minus?
Because df by d theta is not dg by dr. It's minus dg by dr. Oh no,
why? Why? I suppose that we have just
you're right. So since we also change, you know, this
we have some like this. Yeah. Okay.
Good.
And this is the integral of the derivative, and this is equal to 0 since our form omega is with compact support. The functions f and g have compact support, and so this is equal to 0. So this integral doesn't depend on theta. So the integral of f r theta dr is equal to integral of f r 0 dr. So then we can write that this integral is equal to this. By the calculation above, we can write 0 there, and we have inequality that we need. Yeah, that's all, I suppose.
Yeah, good. Any questions from the audience? Okay, if not, then good. So let me also show you what I wrote about that. But well, it's basically the same. There's not much things here. Okay, so we have here R2 without 0. We have this submanifold M. And yeah, so first of all, so the same thing about why the integral over ray does not depend on the angle. Okay, so here it's the point 0. I can integrate along this ray, or I can integrate along this ray. So it corresponds to this integrals over, you know, that Matvey showed me. But how to show that the integral over omega, let's say it's like points well, okay, 1, 0 times theta of omega is the same as the integral over, I don't know, like just any other vector times t over omega. For example, well, that's the only thing we can use is just Stokes theorem, right? So we have the d omega is 0, so we have to use it. How to use it? Well, just draw such two rays and then just find a contour here, like this thing here, 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 and here. And so if the support of omega is completely inside this contour, then well, clearly the integral is 0 because omega is just 0 on all these parts. But even if not, so for example, if omega is like here below, so the integral over any two rays here, so what happens if you write Stokes formula? So this red thing is a support of omega. Support of omega. Then clearly we can find the small part here and small part here, which do not intersect the support. Right? And then, well, the integral over the whole this quadrilateral is 0, since the integral of d omega is 0. Well, and so it means that the integral of omega over any two rays is the same. So here, yeah. So actually it means that, well, so here I just drawn the typical support of omega. And also, as Matvey shown, you can also obtain just by differentiation. But since he already told you how to do it, it's fine. Also, here I have mistake with sign. Indeed, it should be the same. So that's corollary of the fact that omega is closed. And for me, omega was, I think it was, yeah, FDR plus G d phi. Okay, so then it means that this when you wedge your one form with d phi over 2 pi, just averaging. Well, since the integral does not depend on the direction of the ray, so when you take the, you know, this d phi divided by 2 pi, just average by all these rays. And since the value of this integral does not depend on ray, just the same integral over omega, over any of them. Okay, so and well, in general, you see, so this fact is not true for any form. So here we had to use that our form is closed. So it's true only for pairing cohomology. And well, if you wish, it's just because of the Stokes theorem. Then next thing, how to compute the Poincare dual to a circle. Okay, so here we again have R2 without 0, and here we have a circle. How to compute its Poincare dual here.
Well, just the same. If we have, like, I don't remember, just a compact Poincare dual, then we could just like shrink our circle to something very small. So if we want to compute, to check the definition, the question was to prove that it is just 0. The closed Poincare dual is just 0. And well, because we take forms with the compact support, then we could just shrink the circle to the very small circle that doesn't intersect this support, and then the integral over circle would be just 0 of
Yeah, so as you say, so
by the Stokes formula.
since we have since we have Stokes formula, it also gives us the fact that if we deform the variable, the manifold, so here we have such circle and we have a smaller circle. So let's say that gamma epsilon, that's gamma 1. So for a closed form, the integral over gamma 1 is equal to the integral of gamma epsilon, right? And so indeed, so if gamma belongs to, well, class to cohomology with compact support, so it means that we can choose this gamma epsilon so small such that the integral is 0. So it means that actually when you integrate it over a circle, that's true that the integral is 0 always. So it means that for like Poincare dual, you can just take 0 form. The compact Poincare dual, no. The closed Poincare dual. But also there is a compact Poincare dual, right? So it means that we want to integrate just any form, any closed form. It's compact Poincare dual. What to do in that case?
Well, that case is like the case by Matvey. We again have the fact that integration over any circle, integral of closed form over any circle is the same. Yeah.
Mhm.
And then it's variables division of integral. I don't.
Mhm. Yeah, but so what should be the compact Poincare dual? What is the form?
So form the R multiplied by the function that has integral 1.
Yeah, so here and such that the integral of ff is 1. Okay, so and it corresponds to the following. So here you have just a circle, let's say, and this is so this form does not depend on phi, so it's actually just a form which concentrated near this circle. Okay, so it just lives in a small neighborhood of a circle, and then again, so if you have just any form and you multiply it, or you wedge it with eta prime, so actually you just average the computation of integrals of the circles, and since this integral is 1, so the average is equal to any of them. So it will be equal to the integral over omega of S1. And so here, you see, so here we can choose omega prime, which lives near given circle. So you see, so actually we can construct such a Poincare dual, compact Poincare dual for any circle. So it means that we can choose here just another circle. Cohomologically, we obtain the same class, right? Because these circles, they belong to the same homology class. So homologically, if we were just the same, so all these forms, eta prime, they have the same cohomology class. But we have a freedom to choose the representative. And we can choose a representative close to our submanifold, to the circle in the given case. And also here we have a map from first cohomology of R2 without 0 to the first cohomology of R2 without 0. And this is so they're different. So let's say, so here, what is the first cohomology of R2 without 0? That's R, and this is also R. But these are different R's. How to put it? Okay, so what is the representative of the what is the generator of the right hand side? So a generator for the left hand side we know. So just for example, a form as I draw here. So for example, it's this f of r times dr. What is the representative of a generator for the right hand side?
Div theta.
Yeah, for example, you can also divide it like that. But well, that doesn't matter. But yes, and so you see they're different. So here this leaves, let's say, in R direction, whatever it means, and this guy it leaves in like that direction, whatever it means. So it means that from the point of view of cohomology and cohomology with compact support, this like R2 without zero is two completely different spaces. They are different. And you see, also we have a Poincare duality, because indeed, if we pair these two forms, we have the R d theta. So it's kind of also satisfy our idea of pairing. Okay. Good. Any questions about these examples? Okay, no questions. Then let's go to the next topic. That's a compact vertical cohomology and integration along the fibers. Okay, so here we'll define a new type of cohomology. So for vector bundles. So as you remember, vector bundle, it is just a manifold such that at every point of this manifold, we have attached certain vector space, linear space. Okay, such that it changes continuously when we change the point. For example, we can define it using gluing maps. So over every point, over a small neighborhood, this bundle is trivial. So it's isomorphic of 2u cross Rn. And when we go to another chart, then we have transition maps which glues fibers preserving linearity. So that on every fiber, we act linearly. Well, why it's important? Because we want to, we want such that differential of this map is just well, a linear map. Okay, so let's suppose we have a bundle. So that's a bundle E, and note that E is not compact, because fibers are not compact. And so for E, we have different cohomologies. We have cohomologies, just usual cohomologies of E. We have cohomologies with compact support. And also we'll define cohomologies with compact support in vertical direction. Okay, how it's denoted? Like that. Cohomology with compact support in a vertical direction. Well, and it means exactly what you guessed. It means that we consider forms on E such that the restriction, so here take any form, and it means that for any fiber just a pre-image point. Let me also denote. So here I have E projection P. If I have a point X here, then its pre-image is called the fiber over X. And so that for every X, the restriction of omega on the fiber has compact support. Okay, so we consider such forms, and then we want to define cohomology theory of them. And well, we can, right? Because if we have such a form, then its exterior derivative is a gain of such type. Right? So if you restrict the form on a fiber and you compute the differential, well, it commutes with restriction to a fiber. And well, so there is a cohomology theory. And next we can ask, okay, what is the relation with cohomology theory with previous two? So with cohomologies with compact support and with usual cohomologies. Well, and to do that, it's better to define certain maps. Well, we have a map from E to M. Well, and then we can define also projection maps. So let's define the following way. Define the integration over fiber map. Over fibers map. So it goes as follows. So if we have a form, well, any form, okay, locally, consider a local picture. So locally we have a manifold here, that's M, and let's say that here we have coordinates X, and here we have fibers. Let's say in fibers we have coordinates T1, Tn. So it means that we consider, let's say, the manifold of dimension k, and then the vector bundle will have dimension k plus n. So it means that the preimage of every point is Rn. And I want to define a map. This map will go from forms over E to forms over M. And here I have star minus n. Okay, so, well, it means that, well, if the fiber has dimension n and I integrate over the fiber, apparently instead of, let's say, k form, I must, well, k plus n form, I must have k form after that. So how it works? So let's denote this map by pi lower star. Okay, so it's kind of projection. So let's also say that here we have pi. Well, maybe it's better to denote all this pi by pi. Here. Okay, so how it works? So we need to define it on forms. So any form on, okay, here can be presented as a certain form phi times certain function f from the variables from x to tn times dt1 dtk, or phi times f times dt1 dtn. So here I mean that in this presentation I have not all indices. And here I have all. And then, well, let's define pi lower star on the forms of the first type. Just send it to 0. And any form of the second type, we send it to the following. So we have, okay, the form phi is a form on M, right? Because phi, it contains something like dxi and so on. And here we send it to phi multiplied by the integral over f of here x t dt1 dtn over the fiber. Okay, so here it means that for every point x, what I do, I look at the form and I present the form in this basis. So dxi wedge f times this one. And this function f, they depend on x and t. But for any given x, I can just integrate over all this t. If I have exactly an elementary differential of dt1 and so on dtn. And I say that if I don't have all of them, then the integral is 0. And if I have all of them, then the integral is just, well, the integral. And the integral is defined exactly because the restriction of such form on any fiber has a compact support. So I can integrate this function f because it has a compact support for any given x. For any given x, it has a compact support. Okay, so that's the map by lower star.
I'm sorry, we are integrating by the pi minus 1 of x, by the fiber. Yeah?
Yeah, it's pi minus 1. Yes, right. You're right. It's not pi 1, it's pi minus 1 of x. Yeah. Over the fiber. Over here. Okay, now, so what we did, so we defined such a map in a chart. But maybe if you have a different chart, then it will be not the same. But now you can check. So the claim that pi star does not depend on a chart. U cross Rn. So what I mean, if I have two charts here, U and V. So here you have U cross Rn. Here I have V cross Rn. And then they take a point intersection and integrate it in two different charts. Then what happens? Well, by definition, I have the gluing of the fibers with a linear map. So it means that in each of these like charts, I just need to compute this integral by multiplicating this by certain matrices. But okay, you can check that it's just the same. So it just the formula for the change of variables. So this thing the numbers, they will differ exactly by the difference how phi will be different in different charts, right? So because when we change the coordinates, we have presentation of our form in U, a presentation of our form in V. And so when we change the coordinates, we have certain map acting on forms, just another coordinate presentation. And also we have to change things for C. But how we change both of them, it will be consistent. Okay, so let's say it's exercise. Exercise. Right and coordinates. And so because of that, people just usually write it like P star of omega, that just the integral over omega over dt1, dtn. Well, not like that, but over the fibers. Okay, so next claim. Also, okay, that's not quite correct. So does not depend on the chart if the transition function preserve orientation. Which makes sense, right? Because, for example, you have a Möbius band and you integrate a form over a fiber. So if you go along the Möbius band, return back, so your integral will change the sign. So it means that if this gluing map of different fibers, they don't preserve orientation, you will not be able to define the integration over the fibers, because sometimes it will change the sign. So you actually need as you remember, so when we have this formula for the change of variables in integration in Rn, actually just multiplied by the absolute value of the Jacobian, right? But when you go to the integration of the differential forms, then you don't multiply by the absolute value of Jacobian, you multiply just by Jacobian. And in this way, also, so the coordinates will change like in two different things. And if you don't preserve orientation, you will have extra minus sign. So all constants will disappear, but minus sign will remain. And well, that's bad. So it means that it's true only for orientable manifolds. And so here's a small remark. So let's say that remark. We work on vector bundles, well, oriented vector bundles. So all the transition functions are preserved for orientation. Otherwise, well, we'll have some problems. Also, there are ways to somehow deal with these problems, and you can read this in a book. That means that you should just tune just a bit your forms. But okay, not for now. Okay, so we define the integration, and now what are the properties of this integration? Well, theorem is that integration of the fibers by lower star commutes with the exterior differentiation. Well, so it means that just pi star d is the same as d pi star, right? So it means that you can take the derivative inside the vector bundle and then take it as projection, or you can first project and then take the exterior derivative. Well, how to check such a formula? Again, you just check on forms of both type. So here we have a form without all dt or with all dt, right? So now let's just briefly discuss why it's true. Okay, if you already have all these variables dt in your form, then when you perform the exterior differentiation, you don't differentiate f against t, right? Because you already have this full set of dt. So you just differentiate it by dx. And then it will be just the same as if you first project, well, if you first integrate over the fiber and then take d, because you would just the same formula for f. Okay, so what happens if you do this for the form of the first type? So it may happen that you had all dt except one, right? So it may happen that here you had something like dt1, etc., dt n minus 1, everything except the last one, right? And then when you compute the exterior derivative, you will have dtn also. And then when you integrate over the fiber, it seems that it may be not zero. But no, because when you compute this derivative over dtn, it means that you consider here will be f times df dtn, and then you will integrate it over the fiber, okay? But your function f has compact supports. So it means that if you have a function's compact support, then you differentiate it by dtn, then you integrate it over the whole Rn, you will have 0. So that's a say. So the only fact which you need, so the only non-trivial part is that if f has a compact support, then the integral over Rn over df dtn is 0. So that's the only thing you need. Okay, any questions about this thing? I'll skip the details because it's all the same as we did for computations, the cohomology with compact support for Rn. So it's kind of almost the same.
It was a Poincare lemma for compact
Yeah,
technology of that, yeah?
Yeah, it was called
Okay.
Poincare lemma. Yeah. Okay. Now, so it's kind of we study the algebraic properties, right? So we said, okay, we define this integration, and it does not depend on the local chart. Then it commutes with differential. What else? We also need to understand how it behaves when we multiply by forms. And so that will be just another theorem. And so it's called projection formula. And well, I will write it this way. So if we have pi from E to M, so that's a vector bundle, then so we have a form omega on E. This CV on E, and we have a form tau on M. And then we can do the following. So we can multiply tau by the pi star of omega, right? And also we can multiply omega by the following. So we can consider pi lower star of pi upper star of tau times omega. Okay, so that's the formula. So because so if you have omega on E and tau on M, we also have map P upper star. That's the usual pullback map, which acts from forms on M to the forms on E. Right, but then when we multiply it by a form with compact support here, well, by multiplication, I mean just wedge product. Okay, so here, if you wish, we can write wedge product. But let's write just multiplication for shortness. And then it has a compact support, right? So when we multiply a form by a form with compact support, the result has compact support. Well, the same is along fibers. And if you saw this form above, that's a form in CV of E. And so we also can integrate it along the fibers. So that's the projection formula. So basically it tells us that any diagrams that we write here will become commutative. And what else? So, and also something about integration, right? Because so we want to have some kind of Poincare duality. And so we want to integrate forms, want to have commutative diagrams. And about integration is follows. So the integral over E over P upper star tau wedge omega will be the same, the integral over M of tau wedge pi lower star omega. Like that. Okay, so so what happens here? It means that if we have tau, which lives on M. So it lives, here it's M. Here we have tau. And we integrate over M, tau wedge the integral over omega along the fibers. Then it's just the same as the integrate along the fiber, well, integrate over E, omega times pullback of tau. And you see, so that's just Fubini's, well, that's Fubini's theorem locally. Okay, so the second part we don't need even to prove because that's just Fubini's theorem. And the first part, well, so here again, we just need to check it for two different types. Check for two types of forms. Okay, so you remember, so if omega is of first type, then its integration over fibers is just 0. And so what is that? It means that omega does not have all dt. It has less dt than n and than all of them. But if you multiply it by pi upper star of tau, the pullback of tau, does not contain any dt, right? Because it depends on m. It depends on dx. So for the forms of the first type, just 0 on both sides. Then if omega has all dt1, dt2, dtn, then what happens? Then here in pi lower star, you just integrate it over the fibers. And what happens on the right? Well, on the right, you first multiply it by a certain form and then integrate over the fibers. Okay, but so this form, kind of the coefficient which does not depend on t, it's preserved. So if we just look at the definition of integration, so here, so this phi is just outside, right? So it means you just can put out of the integral because this, well, in simple words, this p upper star of tau does not depend on t. So it depends on x. So when we integrate over t, it's just a constant. Okay, and so, well, so that's it. Okay, so also the way to prove it, you just prove it locally. So you write local coordinates and you do it. Then it's even more apparent. Okay, any questions here? Okay, then now we are ready to state this Poincare duality and for this kind of forms. So first of all, there is a version of Poincare lemma. Poincare lemma. For compact vertical support. So this is just, well, pi star is a map from cohomologies of M cross Rn to star minus n. No, so here just any. Is isomorphism. Well, or in general. So it's called Thom isomorphism. Is the same when we have cohomology with compact vertical support of any bundle to cohomology minus n of m by m oriented. it's also isomorphism. Okay, how to prove it? Well, the same as usual. We just need to use Meyer-Vittori's sequence. So we say that we have this sequence of forms. So here we have CV, E, U, union V, omega CV. And here you have the same as intersection. To 0. Well, so here I have just U, V, and this bundle over U, bundle over V, and bundle over intersection. And then I have these formulas, and I prove it kind of by induction. So from here, I write this long exact sequence in cohomology. So here it's E union and then here by integration I have a map to cohomology of M. Okay, so here not M but U intersection, well, U union V. And so on. And so the proof is always, so first I know the fact for N, and then I use the fact that if I know it for U and for V and for the intersection of U and V, then I know it for the union. Why? Because, so if this old diagram is commutative, and here I can use 5 lemma. So let's remember that if you have this maps in commutative diagram, and you know that like here I have 1, 2, 3, 4, which are isomorphisms, then I know that the middle one is also isomorphism. And this maps on the left, on the right, that will be maps like here for the U, for the V, for the intersection of U and V. So the only thing that I have to check is that the diagram is commutative. And okay, so here, so one needs to check that the diagram is commutative. Well, how you do it? Well, as usual. So you need to write explicitly what is this Meyer-Vittori sequence. So how you pass from a form on from the union to U and V and to the intersection. And basically what happens is that you multiply a form by the partition of unity. And then, so what is the claim here? That we can first multiply by partition of unity and integrate by the fiber, or we can first integrate by the fiber and then multiply by a partition of unity. And also sometimes we have this d rho u, right? So because in this maps for Meyer-Vittori sequence, but this forms d rho u and d rho v, they live on M. So again, so it just the integration over fibers does not change anything for them. And so because of that, the diagram is commutative. Well, you can write certain formulas for that, but I don't find them explaining anything. So, well, I can write you a formula. So it's something like pi lower star d upper star v omega equals P upper star D rho U times omega D rho U times P lower star omega equals D pi lower star omega. So that's the map from the migratory sequence when we have this D upper star. Okay, that's from migratory sequence for homology. And okay, so that's on top. So in the bundle, and here it means that this D on M. So it means that you can first go by row in the migratory sequence, then take the integration, or you can first integrate and then take D. Well, you just explain what is D upper star omega. It means you just multiply omega by D rho U, because you see, so D rho U, that's a form in the migratory sequence on M. So, but if you write migratory sequence on the fiber, on the vector bundle, you use this one, you use pullback of D rho U. But then you say that, well, so you can just put it out of this integration because it does not depend on T. And well, then it becomes this one. And all other maps are just restrictions and so on. So that diagram is commutative. And then using 5 lemma and all the standard arguments, we have this Tom isomorphism, which is nice, right? So note that here we have this cohomologies with compact support, with vertical compact support. Any questions about Tom isomorphism and its proof? Are you here?
Yes, no questions.
Okay. So I don't write the details, but I think it's clear what happens. So what's the next important thing? Okay, so we can ask, okay, so we have an isomorphism, but you see it's from homologies of different, let's say, degree. So it means that there is a certain class which gives you this cohomology, which gives this isomorphism. No, in another direction. So how to get the preimage of a class in M in cohomology of E. Okay, so let's call the Tom class. So I want to have a map from H upper star M to the H upper star plus N E, right? So here I have any form omega. I want to understand where to send it. Well, I want to send it to pullback of omega, wedge F, where F is a certain class on E. Right, so that should be a certain class on E. So what we know about this class? So we know that pi lower star of F is 1. So it's a constant, right? So it means that it's a certain form which depends only on dt. So just a form such that the integral over every fiber is just 1. Okay, so do we need something more? No, right? Because, okay, so we constructed just also isomorphism. So we just, so if you take a form F such that this is true, then that's enough. Right, so is it clear? Yeah, so because so it means that we So the different forms, they go to different forms. That's just isomorphism. So that's also isomorphism. So maybe the only question why it's inverse to the Tom isomorphism. But okay, so we just need to check that the pi. So if you first apply this isomorphism, then go back, then it will be the initial form. So it means that if it takes this pi upper star omega wedge f, this will be omega. So that's the only thing to check. So it's inverse to the Tom isomorphism. So why is that? Well, so we take a pullback of omega, then wedge it with a form which depends only on c, then integrate over c. Well, just the same as omega wedge pi lower star pi f. Right, because we integrate over t, and that's just one. So yeah, so that's true. Then also note that pi restricts to any fiber to the generator. Right, because you want to have a form with a compact support of top degree, so degree n, such that the integral is 1. That's exactly the generator. And that's enough, right? Because that's exactly what we need here. Right? Because when we take the integration of the fiber, so for this f, we only need this condition, nothing else. And this condition exactly this, that it's a generator in each fiber. Okay, what else? Okay, now why did we need all that? Because we wanted to have kind of representation of Poincare dual. So point of view, okay, now relation between Poincare dual and Tom class. This follows. So again, you have M, and that's M. And inside this M, we had a submanifold N. And as you remember, we said that we can choose its compact Poincare dual. Okay, so let's say that N is compact for now. We said that we can choose a form with support in the neighborhood of N. So we can choose that eta prime Poincare dual such that support of eta prime in a neighborhood of N. But now actually we have a better way to do that, because as you know from the course of smooth manifolds, or just from your intuition, that there is a so-called tubular neighborhood. Of N is let's say diffeomorphic to the normal bundle of N. So what is the normal bundle of N? It's the following. So here you have M, again here you have N, and at every point here you have two tangent bundles. So you have tangent bundle to M at this point, And also you have tangent bundle to n. So the factor bundle, it's called the normal bundle of n. So the normal bundle of n is Tm factor. Okay, so how to write it? Is Txm factor Txn at x. So I just describe the fiber over every point. Why you can do that? Well, you should prove it. So if you have just one bundle over manifold and you have a sub bundle, so it means that at every point you have a subspace, then you want to say that the factor is also vector bundle. How to do it? Well, we do it locally. You say that, well, you have a certain neighborhood of a point. At every point, one bundle, well, the bundle is just trivial. So for example, just two-dimensional at every point. And then also so at every point, there is like some sub-bundle. And all that changes continuously. Then, okay, so here you define the factor. And then if you have just another chart, you just show how to define transition maps. And I think the transition maps are just a part of the matrix. So if you just you had the transition maps for the bundles, like for big bundle Tm, and when you factorize, you just kill a part of this matrix, because at every point you have just a linear map. And previously it was given by a matrix, and now you just kill part of this matrix. So I think it's like that. Or another way you can do it the following. So you can say that, well, so introduce any metric. Introduce any metric. And then this normal bundle in just the orthogonal complement. To Txn. Okay, so at every point of at every point for a sub bundle, you have just the orthogonal complement. And again, so if you know the transition function for a sub bundle, you automatically know it for the orthogonal complement. I think like that, it's also fine. So, well, anyway, you somehow define the normal bundle, and then you can show that if you just take very small neighborhood of your submanifold, then it's diffeomorphic to this normal bundle. Again, how to do it geometrically? Again, so just from any point of n, you just send in all orthogonal directions like a geodetic. So you introduce any remaining metric on your manifold, and then locally you can send geodetics orthogonal to n. And then you just show that, well, if your neighborhood is small enough, then all these geodesics, they just span the whole neighborhood of n without intersections, without focal points, and so on. Because the only problem here is like two different intersections from one point to like from another, from different points, they come together. But since you know that in the remaining manifold, it's not the case locally, because it's like up to second order terms, it's just the same as Rn, and in Rn it's fine, it's like that. Then, well, that's how you prove it. The fact the normal bundle is diffeomorphic to a tubular neighborhood of n. Is there any questions about normal bundle? Oh, it's fine.
It's fine.
Okay, good. So what I wanted to do, I wanted to say that, okay, so We know that we can ask the Poincare dual to even manifold to live in the neighborhood of n. So it means that we can ask it to live in a normal bundle of n, right? And so it means that, well, so what is that? Also, it has a complementary dimension. Well, so now I claim, so the goal of all these exercises is that the Poincare dual of n is the Tom class of the normal bundle of n. So this Poincare dual of n is just, well, it's G F I, where the G is a map from the following. So G is a map from homology with compact vertical support here plus n minus k, that's the normal bundle, to this one. So that's just normal bundle. That's inclusion. So this G is so this one. So the tubular neighborhood of n, U of n. Here is a map G from this normal bundle. Which I denote here as T. So G is a map from T to M. That's just diffeomorphism. So I have G lower star, just inclusion. So here for cohomologies. And then I say that if I want to find the Poincare dual, I just take the class 1 of my, well, just a constant. And then take this Tom class phi as I defined above. So here. So why is that? So I need to prove something, right? So I need to show that indeed it's Poincare dual. Okay, so let's try to do it. So what is Poincare dual? Poincare dual is the following thing. So need to check. So first of all, I have an integral over the n of the pullback of any form. It should be equal to the integral over m of any form which eta, right? And now I say that here I can use this one. Okay, why I can do that? So first of all, I can reduce this to the integral over the normal bundle, right? So here, because anyway, phi is 0 outside of the normal bundle. And I want to say that it's, okay, but what happens with omega? Right, so here on the, I have F, but here, so what I want to say. Okay, so here, okay, so I want to understand how to write the, let's say this G, G upper star of omega. Okay, so what is that? How to write it? Okay, so first of all, I have I, which is a map from N to T. That's a normal bundle to N. And I just want to have the same I, right? So I want to relate this G upper star of omega and I upper star of omega. So I have the same I, it's just the same. Also, I have pi. Pi is a map from N to N, or from T to N. That's just projection. And now I claim that actually G upper star of omega is just pi upper star I upper star omega plus certain form d tau. Why is that? Well, because this I is the homotopy equivalence, and this pi is also homotopy equivalence. So it means that when I apply to the same class like pi and I, which is just the same J, in cohomology, that's just trivial operation. So it means that it can it can differ only by a closed form. Okay, because I go back and forth. So in cohomology, I did nothing, but maybe I just added something closed. Because I just restricted my form to a tubular neighborhood, and then I want to have it here, and well, okay, so how to write it? It's just integral over t, and here I have pi upper star I upper star omega plus d tau wedge f, and that's almost an integral over n. But okay, now it's still the integral over t, but here I have this f which lives on fibers, and okay, I want to say that I can cancel d tau, because integral over d tau which f is the integral over d tau which f, which is 0. Okay, and then, so you see I have here this pi upper star e omega wedge f. Okay, now I can reduce it to n. I just say that it's I upper star omega wedge pi upper star f. That's exactly this projection formula. So you remember that we can integrate over vector bundle, or we can integrate over the base of it. So we have this pi lower star f, and that's all, because that's the integral over n over I upper star omega, because pi, well, because the integral of phi is 1. Okay, so that's it. So it means that, well, we proved what we wanted to prove, is that if you have, so let's go back to the first example, well, to the example here with the circle, that if you want to have a Poincare dual for a circle, so what you do, you just draw here some tubular neighborhood, which you treat as a normal bundle, and then you just consider. So here, this form phi will be exactly this FDR, right? Because it was just small form, which depends only on fiber, because here the fiber were in direction of R, and with integral 1. That's what was F. And well, here, so here a closed Poincare dual is something more complicated. Okay, so if it's a closed Poincare dual is something not local. But the compact Poincare dual is something local. Okay, what else I want to tell you? Well, maybe just 2 examples to consider. So, example is that you have a manifold M and you have a point. Okay, it's P, that's manifold. And what is the Poincare dual for that? Well, as you remember, we just should take the normal bundle. And normal bundle for P is just the whole neighborhood, right? So the normal bundle for E is just Rn over a point. Okay, so that's just a bundle with a fiber Rn, but the base of this bundle, here just 1 point. And then we need to take a form which with compact support on all fibers with integral 1. What is that? Well, it's just a form which lives in the neighborhood of this point P, N form. Let's say omega, such that the integral of omega is 1. So that's the Poincare dual for a point. That's a bump and form. Then what is Poincare dual of manifolds? M, and submanifold is just M. Well, then the normal bundle is trivial. So at every point, its fiber is just 0, right? Because it's the factor above, the factor of tangent bundle to M and tangent bundle to M in our case will be just just 0, because it's just the same bundles. So it means that here the normal bundle is just 0-dimensional. And so it means that if we have a Poincare dual of M, its Poincare dual is just a function. And for example, a function 1. Which makes sense, right? Because if you have a manifold and you take itself as a submanifold, then it should be paired with a constant. So the dual to it should be some constant function. And well, that's a constant function. And well, so, and if you have something like that, for example, for a torus, so the same here, if you take some curve on a torus, then the Poincare dual, it lives in a normal neighborhood. And so you just choose a form which is 1 with integral 1 over all these fibers. And this is all. That all works for oriented bundles. So if your bundle is not orientable, then well, it's a problem. Okay, finally, so just application. I will not talk about it in details. Intersection of manifolds of homology classes. So just imagine that you have 2 submanifolds of a bigger manifold, right? And prime, and they will have complementary dimensions, right? And then suppose that they intersect transversally. So at every point of intersection, your picture is just the direct product. The tangent bundles, they span the tangent bundle of the ambient manifold. Then what you can do, so instead of just intersecting points, you just say that instead of intersecting n prime, just look for the integral over m of their duals. Right, so you remember, so what is the Poincare dual for one manifold? Just this bump form which lives in a neighborhood and which propagates along this normal bundle. The bump form, this Poincare dual for the next, for another manifold, just the same, but in this direction. So when you wedge two such forms, they are zero almost everywhere, except where? Except the intersection points of these two manifolds. And if they're transverse, it means that these two forms, their product is exactly the standard N form. And then what you know that the integral over the first form is 1 over every fiber. And integral of another form is 1 over any other fiber like that. So it means that this integral will be 1 near each intersection point. Okay, it may be 1 or maybe plus minus 1 because of orientation issue. But it must be 1 up to sign. And then that's how you can define the intersection index of two submanifolds. You just say that, well, I don't know what is the intersection index, but I can integrate two such forms, and then I know that secretly that's just the same as the intersection of two manifolds. Okay, well, that's all I wanted to tell you today.
Okay, and now we aren't talking about the meaning of this in terms of the cup product and the cohomology, yeah?
In terms of cup product, so you mean that if you define the homology theory for cycles, and then you define a cup product in singular, what do you mean?
Yeah.
Yeah.
The meaning of the cup project, the meaning of cup product and the singular cohomology of the co-cycles that are dual to some cycles by the Poincare for the singular cohomology theory. The meaning about the wedge product of forms. We will talk about this later, yeah?
No, we will not talk about it later. So later, okay. So that's all about manifolds, actually. So that's all I want to tell you about Poincare duality. So next, I want to switch to this Czech cohomology and then to spectral sequences. So,
okay.
And so how to relate it to cup products?
The question was like that in our course, the RAM cohomology is not ring, it's just like
So
graded abelian group, yeah?
Yeah, well, it's a ring because you can multiply the classes, but so we don't study that. So if that was the question, so okay, I understand your question now. So okay, that was example of the following. So if we know what is homology, if we believe that homology with compact support is just the same as homology, then here is the relation. So the intersection of two homology classes of complementary dimensions, that's the same as a product in cohomology, this wedge product. And then if you now if you believe that the RAM cohomology is the same as singular cohomology, then I think in this way we can prove that it's the same as the cup product. Maybe not. No, so here we actually needed that this intersection are transverse and these classes are realized as submanifolds and so on. But when you define all these products in cohomology, or like singular cohomology, it's not like that. So it's No, okay, so it is the same, but the proof is not like is not that it's obvious, because in singular cohomology you define them for for singular chains, and here we can do it only for submanifolds. And can we realize a singular chain as a submanifold is not clear. So like locally, yes, globally not.
Yeah, the question was exactly about this.
Okay. The theory of forms, it's good for like smooth manifolds and smooth submanifolds and all that. So it's okay. Okay, let me stop recording.